Okay, today we are going to talk about linear approximations, which is an application of the derivative. And I want to first remind everyone what we did in Lab 6. We were given this function, f of s equals 1.1s plus 0.05 s squared. And we were basically asked to determine exactly or approximate f prime of 30 using the function. So remember, this is the braking distance. All right. So we said the units would be in feet per mile an hour. In other words, how long it takes to brake given how fast you're going. So f prime of 30 is in essence what how much more it would take when you're at 30 miles an hour, a small increase in your speed. How would that affect at your braking distance? So clearly it's going to be different if you're at 30 miles an hour than if you're at 70. That kind of instantaneous rate of change of braking distance with respect to speed. So if you recall, we approximated this using just f of 31 minus f of 30, all right? Because recall f prime of 30, technically it's the limit as h goes to 0 of f of 30 plus h minus f of 30 all over h. But if we let h equal 1, then what we get is precisely f of 31 minus f of 30. All right. So in this case, we were using basically average rate of change, the rate of change of braking distance with respect to speed from 30 to 31 miles an hour. Since over a small interval, we could approximate the instantaneous rate of change of braking distance with respect to speed. For linear approximations, we're basically going the other direction. So we're saying if we know what our instantaneous rate of change is at a given point, then can we use that to approximate the function value? So let me just give you a graphical example. So if you graphed this function up here, all right, we get something that looks sort of like this. All right, so maybe say here's 30. All right, so if we go ahead and put in a tangent line, all right, so we know the slope of that tangent line is f prime of 30. All right, we've already got that, and what we're saying here is, maybe we want to estimate f of 31. All right, now you may say, well, can't we just put in 31 for s? Of course we can. But there are going to be situations that we'll run into, or at least you'll run into in maybe some of your other classes, where we have information about the rate of change, but we don't have information about the function. So this is one application of the derivative, is that we can use information we know about the rate of change or about the derivative in order to estimate function values. So for example, if we wanted to know f of 31, so we can basically extend using this tangent line. We could say, well, let's just use that, whatever the equation of that tangent line is. We could figure it out. But the point is, whatever this is right here, we could use that to approximate the function value. So let's say we don't know what the function is, but we know what the derivative is, and we can find the equation of the tangent line. This is called basically, this is why it's called a linear approximation. We're using the tangent line at a given point to estimate the value of the function at points close to that point. Okay, so I want to kind of give you kind of a graphical representation or understanding of that idea. So kind of maybe a similar graph, but I'm going to look at some notation here. So let's say we have some kind of a curve. This is our curve for f. All right, there's f. Okay, and we are at some point A. All right, now there's one little notational issue that you should be aware of. We have defined f prime of A as the limit as h goes to 0 of f of A plus h minus f of A over h. So this is minor, but in section 4.1, so remember h was this distance from one point to the next. We called it h, and this was A plus h. So A was this, or sorry, h was this distance right here. In 4.1, don't let it throw you, but they're just going to let h, they're going to call that delta x, which is basically just a small change in x. So we would, instead of h, that distance there would be represented as delta x, and out here we would have A plus delta x. All right, so let's go ahead and put in our tangent line. Just kind of sketch a tangent line here. Tangent at that point. Okay, so there's our tangent line. And if we come over here, so here's A, and this point on the y-axis would be f of A. And then if we come up to this point here, and then again so on the function, over on the y-axis, we're looking at f of A plus delta x. All right. Now, we're going to want to define something here. It is delta f, and it can be approximated by f prime of A times delta x. All right. So I want to show you where this would be on our figure here. So let's first think about what this means. So we know this part, that is the slope of our tangent line. All right, we've got the tangent line in here. Here's the slope. If we multiply this, so this, another way of thinking of this, right, we said this is delta x. So we have this right here. That distance is delta x. All right, so if we multiply that by the slope of the line, then hopefully it makes sense that we should end up basically up here. All right, and so this vertical distance is f prime of A times delta x. Another way to see that, right? If we said that m, that's the slope of our tangent line. All right, now let's look at these. Along this line, we have rise over run, right? So the vertical change is f prime of A delta x over the horizontal change, which is delta x. Those cancel, and we get back the slope. All right, so this is a way to understand why down here f prime of A times delta x. So I haven't actually, this is what I haven't put on the graph yet, right? So here, this vertical distance right here is f prime of A delta x. This distance, if we go all the way up to the function, that is our delta f. All right. So again, it's the change in f due to this. So I'm kind of got this blown up right now, but it's the change in f due to a small change in x. So if we were to kind of shrink this back, this would be a very small change in x. This would be the corresponding change in the function value. The linear approximation means that we can approximate delta f, this distance here, using our tangent line by just taking delta x and multiplying by the slope of the tangent line. So then this piece right here, this difference right there, that is delta f minus f prime of A delta x. It's the difference between basically our tangent line approximation and the actual change in f due to this change in x. So this term right here is basically our error. All right? Because f is curved and a tangent line is not curved. So there's going to be some error, and that error is going to get larger the farther away we get from A. All right, so as long as we stay close to A, f prime of A delta x, this vertical distance will be a good approximation for the actual change in the function. And then this error is just the difference between the two.